Hello, statistics students, and welcome to the first video of the second semester, where we're going to talk about a hypothesis test, going through an entire hypothesis test, start to finish. We talked about little pieces at the end of the first semester. Now we're going to try to put it all together. So the first one we're going to talk about is called a one proportion Z test, called that because we're going to be dealing with a single proportion from a sample, trying to think about a population. And we're going to use our Z-scores to help us sort of decide whether we find evidence for or against particular hypotheses. So this whole second semester, I wanted to sort of start here with the framing is that we're going to be talking about something called inferential statistics. What we're trying to do is sort of infer something about an entire population based off of a single sample. As we've discussed many times, it's hard to actually get all the data from a population. So often what we do is we find a random sample using those good random techniques from Unit 3. And we grab that sample and use it to help us think about, we think the population is centered here or has these sorts of things going on. So when it comes to inference problems, it's sort of done in four chunks. We have four phases: state, plan, do, and conclude. So what does the state phase sort of look like? State phase is to state the hypotheses in this particular case and define variables. Right now, that might sort of seem obvious because we'll be dealing with only one, as you can see, one proportion. So from the problem, it'll be obvious what it is. But as we get further along, we'll see that we end up sort of dealing with a couple of different parameters that we're interested in. Plan is where we are going to choose a method and check conditions. So we're going to state what we're doing. Oops. We're going to state what we're doing. In this particular example, today we'll always be saying we're doing a one proportion Z test. There are more tests that we need to sort of differentiate, make sure we state that, and then check our conditions. And then in the do, we are going to find our test statistic and p-value. And then the last thing we're going to do is conclude. So we're going to make a decision. How do you spell decision? About our hypotheses from the very beginning. So there you go, state, plan, do, conclude. So we're going to do our first problem here involving this exact Z-test. So here we go. We got a report from the U.S. Consumer Product Safety Commission stating that 80% of all American homes have at least one smoke detector. A city's fire department has been running public safety campaign about smoke detectors, consisting of posters and billboards and radio ads. The city wonders if this concerted effort has raised the local level above the 90% national rate. Building inspectors visit 400 randomly selected homes and found that 376 of them have smoke detectors. Is this evidence at significance level alpha equals 0.01 that the local rate is higher than the national rate? All right, so let's go ahead and get into this. So first we're going to state our hypotheses. So we've got our null hypothesis would be that this city actually is the same as the national average. So in this case, P is 0.90. Our alternative hypothesis, well, as we read in here, they want to know, is the local rate higher than the national rate? So we're interested in, is this bigger than 0.90? Where P is the true proportion of homes with smoke detectors in this city. Kind of ran out of room. Usually there's a lot more room for us. You could write out the actual word smoke detector. All right, so that's it for the state phase. So state the hypotheses and state sort of what variables you're going to be using. So P in this case, not P hat, because we're thinking about the population of the whole city. P hat would be about our sample here. Okay, so let's go ahead and continue onward here. So we are going to be dealing with a one proportion z-test. So we want to state what we're doing here. Like I said, there's many different tests, and so stating which one you're doing is important. And there are conditions that we need to check before we move forward. Let's see if we remember them. Why don't you pause the video and see if you can remember what are the conditions to check for proportion sampling distribution. So there are three. First, randomization. That is given in the problem for us here. It says that they visited 400 randomly selected homes. So given, great. The next one, independence. So this is where we're going to invoke that's less than 10% of the population. So we're going to assume 400 is less than 10% of all homes. So we're going to believe that this city has at least 4,000 homes. Cool. And then normality. Do we know that it's roughly normal? Well, when we're dealing with the proportion, the way that we check that, if you recall, is to check the number of successes and failures. So in P, which in this particular case is going to be 400 times, and then P right now is 9.9, which gets us 360, which is greater than 10. That was what we were hoping for. So 10 successes. And then on the other side, 10 failures. So 400 times 0.10, which is going to get us 40. That is also bigger than 10. So check. All right. Awesome. So now we know that we can use this one proportion z-test. Remember, they'll always actually, if they just sort of state it like this, like, hey, is there evidence? It's going to work. The conditions will check out. Either you have to say that it's given or maybe sometimes make these assumptions about independence, but they do want to see it on the page. All right, next step, do. What are we going to do? Well, this is where we're going to start doing some math work here to try to find some stuff. So the first thing we're going to do is we're going to identify our center and our standard deviation for this, okay? If you remember that you have forgotten what those things are, we can go to the formula sheet to help us out with that. And on the second page of the formula sheet, we have here this idea about dealing with one population in terms of a proportion, sampling distribution for proportions. And so we can see here that the sampling distribution should be centered at the same place the population is, okay? And we can find our standard deviation here by using the P that we've established earlier on and finding the standard deviation there. So let's go ahead and find those things. So we know that P is equal to 0.90. And the standard deviation is going to be the square root of 0.9 times 1 minus 0.9 all over n, which is our sample size, which was 400 homes. So when we calculate that out, we get about 0.015. If you wanted to actually calculate it out, you can do that. But there you have it. So that is our center. That is our standard deviation there. And so now what we want to do next is we want to find our test statistic. So the test statistic is our z-value that we're going to find. So recall that to find a z-score, that we're going to go the observation, which was coming up here, our p-hat. What did our p-hat end up being here? Well, it is 376 out of 400. So p-hat is going to be 376 over 400, which is 0.94 exactly, but I like to leave it as a fraction just in case it's a weird decimal, sort of make sure my answers are closer to the right answer. All right, so let's go ahead and find our z-score here. So we got 376 over 400 minus 0.90 all over 0.015, which gets us a z-value of about 2.67. Awesome. So if we were to think about our normal curve here, centered at 0 with standard deviations of 1, because I've standardized this, I'm looking for a z-score of about 2.67, maybe right about here. And we're looking for greater than. The alternative hypothesis says greater than. So we're looking at that area there. So I want to know, what's the probability of getting a z-score that is greater than or equal to 2.67 there? Well, that's going to be 1 minus the probability that z is less than 2.67. Why'd I do that? Well, let's head back over to our z-score table. So our z-score table, remember, always shows us left-hand tails here, always less than. So I was sort of remembering that from last semester, so that's why I sort of jumped into that and did that. So what we want to do now is use the z-score table to try to figure out what is this probability that z is less than 2.67. Oh, I guess technically we should, oh no, we're good. I'm all right. So here we go, 2.67. That's going to be on this second page. So I'm going to flip over, and I'm going to go down the left column here to 2.6. And then I'm going to carry over all the way till I get to the 0.07 column here. And let's see if I can see this very clearly. That looks to be about 0.9962. All right, so let's do it. So that's equal to 1 minus 0.9962, which, quick subtraction, gets me 0.0038. All right, so that's the do step. So sort of coming up with the numbers, the number crunching. Here's the thing. Your calculator can actually do the do step very quickly for you, okay? Let's see how your calculator can find all of these numbers that I just found very quickly. All right, so let's see how we can use our calculator to help us answer the same question as before, which is sort of like what's our different statistics give us as a p-value. So in order to do this, we're gonna go into the stat, and we're gonna move over to tests. This is where we're going to be spending a lot of time this semester, so get familiar with it. And you can see that a lot of things are kind of named very similar to each other. But the good news is that by us in the planning phase sort of stating exactly what we're doing, we should be able to be very clear on which of these things we're going to be using here. So we're using a one proportion z-test. So that is the fifth option down right here, one prop z-test, okay? So that's what we're going to end up using here. You can just hit number 5 or arrow down and hit enter. And we can see here that we have a bunch of things we need to enter like we're kind of used to here. So for this, we're going to go through piece by piece. So P naught there. So that is the p-value that we're associating with our null hypothesis. So in this particular example, that is the 90% thing, but we're going to type it as a decimal. Always type it as a decimal. It is a proportion, not a percentage. So if you type it in as 90, it won't work for you. X is the number of successes, or in this case, sort of like the number of homes that we selected that have a smoke detector in it from our sample. That was 376. And then N is our sample size, as usual. It said 400 in the original problem. And then the next thing says prop and then colon, and there's 3 options. So this is where you get to decide on your alternative hypothesis. So are we saying that it's just not equal to in the alternative, less than, greater than? In this case, we were wondering if this city has a higher rate, so we're going to go with greater than. And color, you could change the color if you want, doesn't really matter. Calculate. Or there's another option, draw. I prefer draw, actually, but calculate can be good if maybe you're just trying to do it quicker. You'll sort of see here. So calculate, let me hit it, and then I'll come back and do draw after this. So calculate, so here our one proportion z-test gave us a z-score of 2.66666 repeated, okay, and a p-value of 0.038. And the P naught is 0.94, N is 400. You can see that those mirror very closely what we found on the actual crunching of numbers by hand and using our z-score table. So these are the numbers that you need to report every single time, Z and P. Let's see what happens if we did draw, though, because it's a little bit more fancy, I think, in my preference. So the good news is if you ever sort of do it and you want to go back and do draw, look at how it saves everything, especially if you're maybe running multiple tests and perhaps just small parameters are changing. So I'm going to hit draw. And so we can see here, it graphs for us the normal curve, okay? And then it shows us a little bit of this shading right here. You can see right there on that little right tail, that's that little bit of shading that I sort of drew in my picture. My picture obviously is not as great to scale as this one. This one I think does a better job at it, but it also tells us our z-score and our p-value. The reason I like using this is, one, if I have the time, I feel like I'm not crunched, I do like to draw the normal curve if I need to, and it helps me realize if I'm like actually answering the question that's being asked here. So since it's talking about higher rates, you know, if I accidentally do all this stuff and do all this work and I look at my graph and I'm like, oh, my shading's over here on the left, that doesn't match the question, I catch that earlier. Or perhaps there's shadings on both ends because it's dealing with instead of a not equal to, since you're supposed to look at both sides of it. So I prefer draw, and it kind of looks cool and fancy. So that is how you can run a one proportion z-test. So it's in stats, just to recap, over to tests, and it's the number 5 option there. We'll talk about some of the other ones that are here. Some of them we'll never talk about, but some of the other ones we will talk about here. So be ready to know what each thing does in the future. So you can use your calculator to do the do step, okay, to find all the numbers that are important here. But there is a word of warning that if for some reason you punch in things wrong and you find all wrong numbers, okay, you can lose a lot of credit. So my recommendation to you would be to show some work on here and then use your calculator to check all of those answers and make sure that things go well for you. So if I were in fact going to be doing the, with the calculator, and I'm on an AP test or on one of our tests, I probably wouldn't write literally everything over here. I might just write that P equals 0.0038 because my calculator told me. I might not draw this I'll let the calculator show me the drawing and make sense of it. So that way I'm spending more time on the things the calculator can't do. All right, let's take it to the last step here, which is to conclude, okay? So we did this actually last semester as well. We talked about what conclusions you can make by comparing your p-value to your alpha level. So if you look back up, it says that the alpha level is 0.01. So here's what I would write. Since 0.0038 is less than 0.01, so that's a direct comparison of my p-value to the alpha level, we can reject H naught. We have statistically significant evidence that the city has more than 90% of its homes with smoke detectors. There you go. So the main things here that you'd be looking for to make sure that your conclusion is top-notch is 1, comparing your alpha level to your p-value. 2, deciding whether you're going to reject the null hypothesis or fail to reject. 3, that phrase, statistically significant, yes, they want to see that. And then 4, that you bring the context back in. We have statistically significant evidence of what? And so bringing that all back in, since you kind of got lost in a lot of just like checking of numbers, is really important here. All right. So why don't we go ahead and move on to the backside. So we're going to try one more here. I'm going to get you sort of started, but then let you finish it off as we hope you feel confident in this. So this time around, we're dealing with some census data for a certain county shows that 19% of the adult residents are over the age of 60. So suppose 72 people are called in for jury duty for a set court case, and only 8 of them are over the age of 60. Does this provide evidence at alpha equals 0.05 that the jury selection process is somehow biased and the proportion of elderly residents selected is different than that of the population? So something I didn't talk about last semester and is going to be really important here is that there are sort of 2 different hypothesis tests. There's a one-tailed hypothesis test or a two-tailed, sometimes called a one-sided or two-sided hypothesis test. This example I just read you is an example of something that is a two-tailed hypothesis test, okay? Because it's interested only in sort of like how far from our null are we sort of expecting? Like how different could it be? Not how much further to the right or to the left, just like how often or like when do we get this sort of extreme in either direction? So the key to determining whether to use a one-tail or two-tail test is all in sort of the wording of the problem. Specifically in these ones, it's the last sentences that let you know. Sometimes it's not, so be aware. So like the smoke detector problem had said that they were interested in thinking that maybe they had a larger proportion or higher than the national average. So that's why we chose to set our alternative hypothesis as greater than, because it's a one-tailed. You'll notice in my shading on that, I just shaded the right tail to it. But this problem, on the other hand, says just, is this sample different? So that's when we would know that we're not interested in just greater than or just less than. We are interested in the not equals to. So with that in mind, go ahead and try working this out, keeping in mind when you get to the do phase and you're thinking about your normal curve. So that's where I was finding all my test statistics and looking at my normal curve. So since the first one was interested only in greater than, I was thinking about just shading that right side. Here, we've clearly established that this is a two-tailed test. You'll have to look at both tails, okay? So spend some time on that. If it turns out, you get the wrong answer when you come in, that's totally fine because this is a learning experience, but we do want you to try to do this one all on your own, noting that it is a two-tailed test. So in your do section, you're going to be looking at two tails. You might only find one z-score, but you can still find two tails, okay? So try it out your best way possible, and then come in with lots of questions, and we will go over this as a class.